Hey everyone, I'm Tanner. Just for some background, if I haven't met you yet, my background is in programming languages and formal verification, and I do formal verification in industry nowadays. I'm working on a sort of independent project I've done with some other people that we call AlgoLean. It's roughly a way of formalizing algorithms and complexity theory using some interesting monads and things like that. So yeah, I'll be talking about, here I'll show table of context. I'll start with some motivation, and then I'll explain monads and free monads specifically, and then I'll talk about how our system AlgoLean works, and then I'll give some examples. I'm going to show BFS, randomized quicksort, and then a simple quantum algorithm that each comes with proofs of correctness and complexity. Sort of motivation. This slide is kind of on the motivation behind this, why complexity theory has been difficult to formalize. It's something that's, in attempts to prove aspects of theoretical CS, it's been very, progress on complexity theory is pretty slim. These are sort of the reasons I came up with as to why. In order to prove things about complexity theory, you need some kind of computation model, typically something like a Turing machine. Writing an algorithm and verifying its complexity at the level of Turing instructions is pretty tedious and not feasible. Whereas in real life, when we talk about algorithms, we kind of describe them at a high level English description and then appeal to the sort of Church-Turing thesis that it corresponds to some Turing implementation, right? So the idea is we'd like to find some sort of higher level abstraction that we could talk about complexity, algorithms and complexity in a way that we can actually count the cost of algorithms. This kind of goes more into that. You can see on the left we have an example machine model where you have states and configurations and PCs and things like that, which it would be very tedious to write a real algorithm or something like that. Here I have some pseudocode on the right that is more intuitively what an algorithm would look like, right?
PC is a program counter?
Yeah, PC is program counter, yeah. So this is sort of the main thesis of how we can think about algorithms in our framework, which is that an algorithm consists of a set of basic operations or queries, and then you compose these algorithms using structured control flow, which is things like sequencing, if-then, loops, recursion, things like that. Basic operations, for example, if you're writing a sorting algorithm, the operation you're appealing to is checking whether one element is less than or equal to another. If you're doing a graph algorithm, you're querying whether an edge exists. Or doing some randomized algorithm, you want to randomly sample an element from some type, or you want to read an entry of an array. So the idea is an algorithm consists of little queries or operations like that are then composed using loops and ifs and things like that. So the goal here is we'd like some framework for writing algorithms over an arbitrary set of primitive operations and then proving complexity of,
Is there also a write?
These are kind of just some examples. But writing is exactly,
I guess it's not type of query, but a primitive operation.
Yeah, it's an operation, exactly, so this is sort of the high-level flow. The idea is you define some query signature, which is what are your primitive operations. You define a model, which consists of the semantics, which tells you what does each operation mean and what does each operation cost. And then you compose them using control flow. Given the program and the model, you can evaluate the correctness and complexity. So the sort of way we define queries in Lean, we use what we call effect signatures or query signatures. These can be described as type constructors. So what we have here is Q is a function from type to type. And here you can kind of enumerate what are your operations. And then, we'll see how we can do this, but eventually we would compose these programs using this do notation where we have let and if, and then we call each query inside. The way that Lean allows you to sequence effects this way comes from the monad abstraction, which is why these are useful here. And then what's interesting about free monad specifically is that given any set of queries, which you as the programmer define, you can get a monad out of it. So that's how you define these queries, and then you get this kind of notation for writing algorithms. So I guess that takes us into, so now I'll explain monads a bit. Here was my best attempt at sort of describing one sentence what a monad is. A monad is given some, if you have a monad M and you have some type alpha, you can think of the type M alpha as a computation which produces a behavior M and returns a value of type alpha. Some examples are, you see on the left side, you have the exception monad, which either will error or return a value of type alpha. You have the state monad, which returns values of type alpha while also maintaining some internal state. Writer will sort of log output. IO performs actions in the world, and reader kind of reads from a existing context. So these are like example monads that follow the same structure. So yeah, to describe what monads are, we have to first describe something called a functor. A functor is, or a monad is essentially a functor with some additional structure. So we'll define functors first. A functor first consists of a type constructor, which you can think of as a function from types to types. So given some type, you get some other type. The structure it contains is something called a mapping function, which you can think of, I think the best example for map is like with lists. So a list is an example of a functor. The map function of the list functor takes a function and applies it to each element of the list. So more generally, you can think of, if you think of a functor as a sort of type of container, the map function applies a given function to every element within that container, right? The laws, these are the functorial laws. If you know any category theory, that's exactly how a functor is defined. It preserves identity and it preserves composition. Yeah. So like I said, a monad is a functor with some additional structure. So you have your map function, and then you additionally have these two functions, pure and bind. I'll explain bind a little more. Pure is pretty simple. Pure just takes a pure value and then embeds it into the monad. You could think of it as like a default behavior in some sense, or like a no effect. Bind allows you to sequence effects of the monad. Here we see how we can derive map given pure and bind, which tells you any monad is a functor. And then these are some of the laws. Importantly, bind is associative. Yeah. Any questions? Yeah, go ahead.
These are monoid monads.
Yes, okay, yeah. So I'm sure you've heard a monad is a monoid in the category of endofunctors. It's actually a very good definition, even if it seems unclear. Here as programmers, we use bind, but in math, when they define monads, instead of bind, they define a function called join, which you can think of as like a multiplication. So if you know what a monoid is, it's something with a unit element and a multiplication. So a monad is a functor with a unit and multiplication, which is what the monoid in the category of endofunctors means. But yeah, bind is convenient for programming because it allows you to sequence effects. But in math, they use the join. Yeah, but good question. Sorry.
I have a curiosity. So multiplication usually have two things the same type, right?
Mm-hmm.
But for bind, it's like MA and then A to MB.
Yeah.
There's a join function that's, maybe you can say the signature of the join function is M.
Yeah. Join is apply the monad twice. So you have M of A, and it gets you an M of A. It sort of collapses the two applications. You can think of that as a multiplication, right? Yeah.
You can either define bind in terms of join or define join in terms of
Yeah,
bind.
you can do both. That's a good exercise. Exactly. You can derive one from the other.
So join's like the more mathematically pure one, but we use bind.
Yeah, we use bind because it's convenient for programming. Yeah, go ahead.
I guess I was just going to say that the programmer's intuition is flatten, and flatten shows up in all sorts of natural use cases in programming.
Yeah,
You don't think of
for
join
sure.
So much, but you would think like, oh shit, I ended up with like the list of a list, so I just flatten it.
Yeah, that's a good example. So a list is an example of a monad, and flatten is exactly if you take a list of lists and turn it into a list. That's the join function. The bind function for list is called flat map, which is essentially you flatten a list and then apply a function to each element of the list. That's your bind for the list monad. Yeah. This explains bind a little more. The idea behind it is that it allows you to sequence monadic effects. I said if M encodes some kind of additional behavior or side effect, bind allows you to compose functions while sort of sequencing that effect through the program. So the idea is like, you have this type MA, you can think of as a single, a program which returns an A and behaves according to M. and then you have this function which takes in a pure A and gives you an MB. So you can think of MA as like the first computation, and then you can think of this function as a sort of continuation, which extracts the value from the first computation and applies the function to that value, right? And then it gets you something in MB. So yeah, like an example, if you have the state monad, if you have some initial state, if you have some initial program which contains some state, call it MX, you would run K on the output of that state and get some new state, right? Similar thing for writer, it just combines the logs. Yeah, that makes sense. Cool.
Is this model multi-threaded operation?
Yes, you could. You can do like things like parallelism and non-determinism with some kind of monad. I don't know exactly how, but I've seen that people have done that. Yeah.
Past or future monad.
Yeah, exactly. Yeah, like in Rust, they have the future operator. That's a monad. I mean, Rust doesn't have explicit monads, but that is a monad. Yeah. I don't know if Lean has futures, but yeah.
It's an abstraction over all sorts of different AI.
Yeah.
Input output. You can do multi-threading.
Yep. So yeah, what Lean and functional programming languages provide that's nice is this do notation, which makes it sort of feel like you're writing imperative code. And really what it is, it's just syntactic sugar over nested bind operators. So you see on the left, you have this program that's pretty hard to read. But in Lean, you can use do notation, and it gets you a very obvious program. Let x equal the value returned by mx. Let y equal the application of f to that, and then just return x plus y. So that function on the left is how you'd write it without do notation. Then you get this really convenient notation. And what's nice about monads is essentially any monad allows you to write in do notation. So if you have a monad, you could do this and sort of get like imperative feeling code. Yeah.
You've seen async await. Imagine that was extensible.
Yeah.
But like if you have a limited number of GPU cores and you want to model the computation, how long that takes? I guess you just need to be able to count how many.
This is just a generic abstraction that you can apply to. Depends on which specific monad you're to answer that.
Yeah, so I'm gonna give a couple examples. Lean has this exception monad, which I mentioned earlier. This is, if you know Rust, this is exactly the result type. So it's saying it's an exception that returns a value, or it might return a value of type alpha, or it might error with some tagged error epsilon. The pure function just returns OK with the value. And then bind, essentially, you're given some, here, let's look through the types. You're given some possibly failing computation here, and then you're given a function which you can apply to the resulting value. What you do is you check if the first value is OK or an error. If it's OK, then you apply the function to it. If it's an error, then you just error early. So it's like if you know Rust, the and then operator for result, or kind of like the question mark. It's the same thing. Yeah. So yeah, here's an example. We have like a parser. It takes in a string and returns either a user or it fails. So what we do here is we let user equal parse the input s, and then if that fails, the whole function fails. Otherwise, we apply this function load prefs to the user.
I swear to God, he ran away.
Yeah, you're good. No problem. Yeah. Cool. Cool. Any questions? We good? Cool. Yeah, state is another example of a monad. So the idea is you have some internal state that you're tracking of type sigma, and then you're returning values in A. So the idea is you're applying functions to A while also tracking some internal state. You could be tracking like names of variables or things like that. Yeah, so I think, we can, I don't have to go through that. But yeah, there's another monad, state monad, that tracks internal state. Sorry.
Just double check your intuition. So the example here is that the reason it's a state machine is that whatever it does from the get, add one and double it.
Yeah, exactly. Yeah. So you're tracking some, like get says, get me what's inside the state, and then you're saying double that, right?
Yeah, I was worried about the dot notation.
The dot.
The
Oh, of the modify? Yeah, that's a partial application. So it's, yeah, you got it. Sorry. Cool. Okay. Yeah, so here's just a bunch of examples of monads. I kind of put them in 4 different kinds. There's control, execution, environment, and metaprogramming, which is nice about Lean. You can also write your own tactics in metaprograms, and these are all in different types of monads. You have a tactic monad, core monad. These are how you write your own tactics. But yeah, this is just an example of a bunch of monads that we have in Lean. Yeah.
And they come with Lean core, right? We can use all these.
These are in Lean core, yes. Yeah. Okay. Yeah, this kind of repeats some stuff I was saying. But yeah, if you have a monad, then you can write these sort of imperative control flow kind of programs. So you have things like if you have a type class called for_in, which allows you to write loops over collections. And you have like while loops and things like that. So yeah, when you have a monad, it allows you to sort of write programs in this imperative style. Yeah, next is free monads. Any questions on the monad section?
Just go back one slide.
Yeah.
Again, just the construction. What that's trying to do right there is just track the best value.
Yeah. Yeah, it's, sorry, one second. Yeah, so you have some value best, and then you go in and just basically keep track of it, right? By looping through this list x's. Yeah.
So is for syntax part of the do notation? Or?
Yeah, so you get it in do notation. There's this type class called for_in, which basically says this is something I can loop over. So like, if I'm in do notation, I can loop over this. That's what the for_in type class gets you.
Every monad gets it, or the monad has to extend
Parameterized
it.
over the monad, and I think by default
Exactly.
it's defined for the common ones, but it's not automatically. The type class takes a monad parameter, little m.
I see.
Yeah.
So you have to extend
Yeah.
your monad. I see.
It's like list, for example. Like given any monad, then you can loop over the list in do notation, right? Because list has this for_in instance, right? Yeah. Cool. All right. Yeah. Now I'm going to talk a bit about free monads. Yeah. So this is a pretty complicated abstraction. So free monads are commonly used in Haskell. They actually did not exist in Lean, and I had to write the entire library for my own use case, and now it's used it's like in the CSLib library. And the sort of reason why it's not in Lean, I guess I'll explain some more after I explain the definition. But the idea is that first the inputs are, you have this type constructor Q, which we think of as our queries in our AlgoLean, and you have 2 constructors, which is pure, which is saying given any value, put it in it can be in the free monad. Then you have this lift bind, which is explained a bit here. Let me go through here. So yeah, we have parameters are this Q. Pure just, takes in a computation and returns the A. Lift bind, you can think of it as having 2 parts. So it takes in this operation QI and it takes in this continuation. So it's saying that's arbitrary type. Yeah, it's, what'd you say?
An implicit in this.
Yeah, I is implicit, but it's a type. Because you see Q is of type to type, and it takes in an I, so this QI is just the type, right? So yeah, op is of type QI, so you can think of it as performing one operation from our query signature, and then cont is a continuation which takes in an I and returns something of this free M type. So you can think of it as receiving the answer from op, and then going on with the rest of the free monadic program. So you get the sort of tree, which I'll explain the structure a bit more because this is abstract for now. Yeah, so you can think of free monad programs as a tree. So I have an example here. Say we have two query types. We have read flag and read nat. Here's an example of a program. You can think of read flag as like, it's some effect performed and returns a Boolean. You can read the Boolean, and then similar thing with read nat. We have this do notation on the left. Sorry, question. Okay, cool. We have this do notation on the left, so it's saying like, let B be read flag, so it's saying read from the Boolean. So B is going to be some Boolean value, and then we're going to, if B is true, then read natural, and then add 1 to that natural, otherwise return 0. You can desugar that, and you get this bind, right? But then you can desugar that further, and you essentially get this tree, which is saying you're going to read the flag. There's going to be 2 options, false or true. If it's false, you return 0. If it's true, then you read the natural, which can be any natural number, right? And then you just return that. So that's how you can sort of think of a program written in this free monad as a tree by just desugaring in this direction. Is that clear? Cool.
I guess what it did is
Sorry.
get us on top of the reader monad. We're doing a bunch of reads because the fact that we're segmenting the reads into two different.
Yeah, I mean you can write, so any existing monad you can write as an example of a free monad. That's, yeah. Like you could write, sorry.
It was just cut off by the screen here. It's like it's read nat because 0 gives you tier 1, 1 gives you tier 2. Let's make sure that wasn't off by 1 and understanding that.
Yeah, so this is not like a super useful program, but it just like shows you, yeah, you take a Boolean, you check it. If it's false, you return 0.
Because
If it's true,
+1 in that syntax.
yeah, if it's true, you read, yeah, exactly, yeah, cool.
Okay, it wasn't like you're avoiding the fact that you could read a 0 and that's a natural number and it would be ambiguous.
Yeah, no, it's just because you're adding the, yeah, there you go, yep.
So you have another example. I sort of feel like I get something about, I don't know, the freeness of it, but just in like this fuzzy way. And if you have another example, that'd be very helpful.
Example of a program like this, or?
Like this, written those different
I mean, I'll be showing several at the end. Yeah. Sorry, go ahead.
I guess so I have some prior experience here.
Okay.
So maybe going to try and help with some intuition.
Yeah, absolutely.
Instead of a program that is going to execute under the rules of Q, what you're getting is a value that is the structure of this. Like you've got a data type that is built up of this program expressing the computation of Q. So you don't actually get run Q. I get a program expressing a program about Q. Things like the task monad or these structures that show up in functional languages like Scala and others, you're getting a program that describes asynchronous computation, and you're later going to run it. It is useful to construct a value that represents the computation, and what you're getting back building up the program as a value, and then getting to run it separately. So the useful thing of a free monad is you're going to build up this large inductive data type, which is your program, and at the end you're like, cool, I'm going to run this. But I assume the usefulness of what you're doing is I got a representation of my program as a data type, and then I'm going to like analyze what's going on.
Yeah, so exactly. What free
monad?
sorry.
The free construction, sort of like a minimal interpreter.
Yeah, I mean it's like I want my program as data. And so naturally, if I'm going to interpret my program, I've got the program as data, and I have some run function.
Yeah, exactly. So like when you have like existing monads in Lean, the semantics is sort of baked into the definition. Like a state monad is tracking state, and writer monad is writing. A free monad is just you are able to construct a description of the program, and it comes in the form of this sort of tree. And then you can interpret however you want by just walking the tree, which is kind of what he's saying, or like folding over the tree, right?
All those things before were pure and bind with functions to actually run the computation. The trick here is just saying I'm just going to turn these into constructors.
Yeah.
Yeah, that's what you meant by turning your whole program to a big data type.
Yeah. The program is just a tree that you can just pass around as data and interpret however you want.
And so you really do separate the parsing or construction from eval.
Yeah, exactly. And then that's sort of what makes it useful for complexity, because if you remember at the beginning, I said we give cost semantics to each query. So then we have this whole tree. We can just go through and count the total complexity of the program. Right? Yeah. Go ahead.
If I create an abstract syntax tree data type in any programming language and write some function that walks it, have I basically created a free monad without knowing that I'm doing that?
It's not a free monad because it doesn't have like monadic structure, but it's a free something. I guess it's like a free algebra over the signature defined by your syntax tree. But it's not a monad because you don't have a monad defined on it. Yeah.
Define monad. And like build your structure with those monad operations in kind of the same way. Like bind is in some sense creating a larger code product of like.
Yeah, you probably could, but then you probably end up recreating this in a complicated way. Yeah.
So is a free monad? Is it a type of monad or is it a generalization of?
It's a type of monad, but it's in the sense that you're given any type constructor or given any functor, you get a monad by applying the free monad to it. Right. Yeah. So it's kind of like in math we have like free groups is like given a set. you apply the free group construction, you get a group out of it. It's the same idea. Given a functor, you get a monad out of it, right? Yeah.
The way to think about it is like the derived macro in Rust, where like you derive the bind and unit operations automatically given some like
Yeah.
data type you have with
Yeah.
the functor.
Yeah, exactly. So it's saying you can build a monad out of any functor, and then the usefulness is that you can just define, like I was saying, define your operations as a functor, and then you get the free monad out of it, and now you can write programs like this using the operations that you defined, right? Yeah. Cool. Yeah, so this kind of explains bind a little bit. So yeah, it's like you sort of have this tree. You can think of this operation Q, like in the last case it was bool. It can return multiple pure values, in this case either pure A or pure A1 or pure A2. And then when you bind it with this continuation function K, then that just basically applies K to the leave. And then K itself produce other free monads, or other, monads, and then you get this sort of finite tree, right? Yeah. So this is a mathematical approach to it. Yeah, this shouldn't be, I hope it's not too intimidating, but this is how it will be defined, like, categorically. The idea is that, it's like any free construction. It's like given some object and you want to freely generate some structure on top of it. This is like, if I were to show you the universal property of a free group, it would be the same thing. It would be replace things with sets instead of functors. But the idea is Q, you have your underlying query functor, your query functor, right? If I have any other monad M, and I have a way of interpreting my queries into M using F, then for free, I get a function, we say F hat, from the free monad on Q into the other monad. So what this kind of tells you is like, if I have my queries Q and I have any other monad M, if I can interpret each query into M, then this lifts to interpreter for all programs written in the free monad over Q. And this interpreter, because of this algebraic stuff, is a homomorphism. So we know that the interpretation of each program is compositional in the monadic structure, meaning you can sort of split it into it's compositional in bind, basically, right? I hope that makes sense. But yeah, these functions end up being really important. So we call f hat lift m, and it ends up being used all over the place in working with the free monads. So yeah.
Oh, that works nicely with the notation because it's got the auto lifting.
Yeah, exactly. So any query in the base functor can be considered a program in the free monad by just lifting using lift. Right, yeah, exactly. Cool. So we saw in the last diagram, we have this function f from Q into the monad. You can think of that as what's called an effect handler, if you're familiar with like algebraic effects. Essentially, the query type that I've been talking about, this underlying functor, is itself a set of algebraic effects. And then this f is a function from each of the queries, so QA into MA, right? And the universal property tells us if this function f exists, then this function lift mf exists, which is a function from the free monad into this monad. So it's a way of interpreting. If you have it's what I was saying before. If you have an interpreter for each query, you get an interpreter for any program written in the free monad on those queries, right? And yeah, this, because it's a homomorphism, this interpretation preserves the bind rules. Yeah. Clear. Cool.
What was M again?
M is just any other monad.
Any other one?
Yeah. Yeah. Because
So we're lifting a functor to a free monad.
Yeah, because your queries don't have any meaning themselves. They're just syntax that you've written. So if you want to interpret them, you're going to say, like, say I want to interpret them into another monad. Then yeah, you give an interpretation for each query, and then you get this function for free, which then interprets any monadic program, right? Yeah. Yeah, this is kind of redundant, but yeah, like if I have some effect signature, in this case we have sort ops alpha, which is used in the library for sorting functions, then the free monad over this allows us to write like sorting algorithms, right? Or in this case, it's the best algorithm we had before. Yeah, so, yeah. Yeah, so now monads and free monads have been covered, I'll start describing how the library works. Yeah, you can think of this sort of overall flow in this one diagram. The programmer's job is to define, if you're trying to define some type of algorithm, you define what are the basic queries of that algorithm. So what I was saying before, like if you want to sort, you need to be able to compare. If you want to do a graph algorithm, you need to be able to check for edges between. So you would define that. And then you give a model, which says, what do each of these queries mean, and what does each query cost? And then you plug that into the free monad, and now you can write entire programs using these queries, and the programs can be evaluated according to their cost and their official, like their final outcome, right? Yeah. So, okay. So yeah, we use this abbreviation prog for the free monad over a set of queries, because this is like the monad that we're writing our programs in, so we call it prog. And then this is our model. So this is saying, give me an evaluation semantic. So this is saying what I was saying earlier, like interpret my queries into any other monad. And as we know, that will then lift to all monadic programs. And then for each query, what does it cost? So you define your queries, and then you define the meaning of the queries like this. Yeah. And then given any program written in your free monad, you can then take its final output by just using this function from the universal property, lift m, and calling it on the evaluation of your model. And then you can do a similar thing with cost, where you return the final cost of the program. Run internally uses lift m, right? So this gets you the final output of your whole program, and then the final complexity of your program, right?
So when we get the cost, we don't run it. It's pure, or
Cost
we
of
run
running
it.
from the eval in some way, like you do the eval and just return the cost because it sort of computes it along.
Yeah, the cost is tracked along. It's like it returns like, yeah, it's tracked along the way. And then, yeah, it's exactly, you just eval it, and then the cost comes out of it, and you return that. And
You can't get the cost without running it. You have to run it.
Yeah, exactly. Cool. Yeah, so one thing we can do is define complexity classes, which is nice to do like real complexity theory with. We can define like basically a query problem, which is like given some model and some type of outcomes, like, yeah, you're defining basically a problem, and then you can say this program solves this problem within some bound, and then you can state like complexity classes, like it solves this problem within bound, polynomial time. And then you can say it's complexity, it's in complexity class P, right? Yeah, yeah, go ahead.
So is cost meant to model just like asymptotic complexity, or could you use it also to compare programs based on like wall clock time?
Yeah, so it's an exact. I mean, so cost is general in the sense that it can be like any commutative monoid, but it's usually just going to be a number. So it's going to say calls this many, but you can still write it as a function of the input size and do this sort of, yeah. But you can also just say like this function, returns like n cost, and this returns, n plus 1 or something.
But it's not asymptotic. It's like.
It's precise, but yeah, you can still state things. You can still state things asymptotically like this. Yeah. Yep.
And then you prove.
Yes, so on that note, like does this method generalize to something that's very concrete and hardware based? Like how many clock cycles on real hardware does it take to execute this specific program? Like is that a path that this can eventually lead to?
I would think so, but we haven't explored it. If you can state those things in terms of some set of queries, and yeah, then this would work.
The cost model for a real processor would be very, very much more complicated than computing classes of n squared or n log n, like complexity classes.
Yes.
That's where I think
But the cost model is just an arbitrary type, which has some way of like adding, right? It's basically like a monoid. So if you can, yeah.
real world processors are more interesting.
It's still within the lean semantics, right? It's not like what's happening on the CPU underneath,
Yep.
right? You're saying
this
freely defined function in lean costs you 1 or x or whatever, but is that going to translate to whatever instructions like underneath? That's you decide.
But could you write a compiler that basically translates that into another monad that corresponds to the CPU or something, and then
You need to like encode your monoid, or encode your assembly as like a monoid. The composition of assembly is a monoid. And then like model all the memory, all the disk, all the caches, the speculative execution, the CPU register state, all of this to like
You
figure
have to
out
write
how-
lean in lean, basically. The lean
We write LLVM and lean, it sounds like, 'cause you have to model the,
Right, the
compiler
hard, embed
optimizations.
the like the Verilog hardware in lean was what you probably need to do.
well, that's what I told the AI to do it, and I put the tweets also. It's not good how-
What
you
was
can
the
see whether it
complexity
actually
class?
succeeded.
You need like the
What'd you say?
86 spec.
Like, I thought we were getting complexity classes, so we'll stay at a higher altitude, I was thinking, but
Solid.
but at that very high altitude, I was meant to say, again, dumb naive question from the dumb naive corner, which is like, P for program, because I gotta say, when I led this slide, and I'm like, you're not saying this is in polynomial time.
Oh yeah, no, that's
very
bad.
tricky.
Yeah, it's bad naming. But yeah, I mean, you could use this to say to
The
state.
bound is not specified on this particular, or maybe I misunderstood your example here, what was the bound you were trying to say?
Yeah, bound isn't specified, but it can be anything. You could say is a polynomial in the.
We'll find out.
Yeah.
So the cost is a lean function, but because it's lean, you can prove theorems about the cost function, and that's
Yeah.
what you're getting.
That's what I was expecting to
And
find.
you
is
can
like,
get
so
to
we-
the complexity classes
Right, that we're
from
gonna
that
do
because
the next step, so we'll get there.
Yeah, like we have this definition solves within, which we could say like solves within polynomial time, right? And then in class is like a class of,
That was
yeah.
basically it. I know you're gonna get to that slide in a second, and then
Yeah,
it's
for
like, oh,
sure.
that's, wait, he means that, a couple
Yeah.
of slides from here.
Yeah. Sorry, go ahead.
Oh, maybe I'm about to jump again. I guess I was curious for some examples of cost that you have used.
Yeah, for sure. Yeah, I will show some. But one thing is like what makes it interesting is that since cost is abstract in the sense that it only needs a monoid structure, it doesn't just need to be addition. Like if we want to talk about circuits and I'm considering circuit complexity, I could look at like circuit depth. And in that case, my monoid is not plus, it's max, right? So there's an example of a cost. Yeah, so we do have circuits in the library, and in that case, our cost model is like maximums on natural numbers, right? Instead of adding natural numbers. Yeah. Whereas in most cases, it's just like you're counting the number of times you had to query for an edge in a graph or something like that, which in that case is just addition. Yeah. So yeah, here's just sort of a list of classes we have defined. It's kind of a lie because the ones in the middle are not in the library yet, but they could easily be defined based on something I'm working on. But we have like P and MP. We have some basic quantum circuit families. But it's literally just plugging definitions into this like solves within, and you can get all these classes. Yeah.
So it's a very funny statement if you want.
Yeah. Or well, no, this is saying that if you have a program in P, like that P is a subset of NP. Yeah. Yeah, you could state the converse, but obviously there's no proof. Yeah. Yeah. So yeah, these are a list of classes that we have defined or are working on defining. Yeah. Yeah, so now I'm going to show some examples. I'm going to show how we can write BFS. I'm going to show how we can write a randomized quicksort, and then I'm going to show a basic quantum algorithm. I don't know if you guys have background in quantum computing, but I'm not going to explain, so you just have to go along.
Possible.
Yeah. So the first one is our graph model. If you're trying to do a graph algorithm, like I've said a few times now, the basic query that you're performing is just checking for adjacency between two vertices, right? So we're defining our query type here. This is our, functor, our underlying functor that we're going to take the free monad over. And the only query is just given to natural numbers, which represent nodes in the graph, check if they're adjacent, right? And right now, like I said, this has no meaning. It's just this syntactic like tag for what this query will be. And then to give it meaning, we give it a model. The model in this case is parameterized over a real graph. So we give it like a symbol graph, which is defined in MATLAB. And we're saying that the meaning of checking if these two are adjacent is by checking if those two are adjacent in the actual graph that it's given, right? Does that make sense? And then the cost of checking if two edges are adjacent, if two vertices are adjacent, is just one. So the complexity of an algorithm would just be counting the number of times we check for an edge, right? Yeah. Yeah, I mean, you guys know how BFS works, but this is kind of the explanation of it. And then I'm gonna pull up the code, which I hope I can screen share properly. Yeah, 1 second. You guys see that? Sure. I can add. Okay, cool. Yeah. Question?
Idiomatically, there are advantages for you of talking about adjacent as that string on the slide, and not going straight to like, hey, these are well-known concepts in MATLAB for graph.adj.
Yeah.
I was just curious, like, whether you find yourself ever conflating the two, or it's important to talk about your cost modeling in different terms. Like, the difference between adjacent and ADJ is obviously one is the actual operation in MATLAB.
Yeah. Wait.
But why?
ADJ is the semantics of the adjacent tag, which is just a tag.
I was saying, if
Right.
you developed a stylistic shorthand as to why you would use the full string in one case. And
Yeah, I guess it gives you a differentiator. Yeah, yeah. Cool. So here's a lot of. Sorry. Should I zoom in? Yeah. Shoot. Let me move all of
Is this
this.
code on GitHub at the moment?
Not this code in particular, but there is a library that I'll show you at the end. This is a local branch. I'll merge it in at some point. Yeah.
can you go one more size?
Yeah.
Can you apply the functor zoom to the screen again?
I'm trying to get this out of the way. Where is the? Okay. Yeah. Okay, yeah, so we like essentially define a bunch of helper functions. We define this structure BFS state, which is just like tracks which nodes have been seen and which nodes are like coming up next, right? And then we define a bunch of helper functions, and you see these have type prog. So these are programs in the free monad, right? And then if I were to desugar these, we would get that like tree I showed earlier. And these are just like he was saying, programs as data. These have no syntactic meaning until they're applied to the model, which gives us the meaning of the, yeah. So yeah, we don't have to like go through all of these in detail, but yeah, this is performing what BFS does, and then this is like the final algorithm. It runs through the list of nodes, writes this helper function, and then returns the state of all the. It returns all the nodes which are reachable from the original node, right?
Could you do some sugar to either hide or auto insert the whole prog annotations? Because I noticed the code itself looks well the same. Like it had been written.
You mean these annotations?
Yeah, like these.
I mean, that's just the definition.
I mean, like,
Yeah.
like you define a function that's written including the type signature, like a plain function, but it's like meant to be in this monad from the beginning.
I don't think I understand.
It's inferred, right? If he deletes it, it will get inferred.
Would it infer it? I mean, you mean deleting like this?
Is that
Oh, let me see what happens. It doesn't know what I'm talking about. I'm sure there's a way I could make it figured out, but yeah. So yeah, this is the algorithm. And then what we do is we can prove the correctness, which is in here somewhere. Yeah, here we go. This is correctness of all the helper functions.
Sorry,
So-
what exactly? Correct.
Yeah, I'm looking for like the final correctness claim, which should be in here somewhere.
But the algorithm itself, because the point you're making is it's just do notation in the same way you would write it.
Exactly. So yeah, that's the idea. It's like we've written this like very imperative looking code in Lean using this free monad. Okay, where's the BFS specification? Yeah, so this is like the specification. This is the correctness theorem. And we're using a framework. I don't know if you guys are familiar with MVC Gen. I would have loved to explain it, but it was going to take a lot of time. But I'm sure Alec has seen it. It's like a way of, it's a monadic program logic that's in Lean core. It's actually pretty cool. It has this tactic called, it gives you this tactic called MVC Gen that allows you to, like, given some monadic program and some like Hoare triple about it, so like a precondition and a postcondition, you call MVC Gen and it breaks it down into verification goals, and then yeah, it's cool. I would have explained all of it, but it's just there's a lot of extra stuff. But what's cool about it is that this MVC Gen works using something called a specification monad. So what's nice is that we can get like weakest preconditions on our free monads by giving weakest preconditions, like giving a morphism into the specification monad, which is given to us by the universal property. So it's another use case of that. There's a lot more to explain, so I'm not gonna, but.
Is it hooked into MVC Gen already?
What? Like,
Like, yeah, writing this morphism into specification so you could sort of use MVC Gen, or MVCgen can use.
Yeah, so if you have a morphism, MVCgen is defined such that if you have a morphism from a monad into the specification monad, you can use MVCgen to reason about it. What we've done here is for each of our like query types, we do the same thing where we interpret each query into the specification monad, and then using Lift, we get MVCgen for free, which is a very nice use case, a very nice like use case of the free monad here. But anyway, so what I'm able to do is like, now that I have MVCgen, I can state Hoare triples. So this is saying that given some starting node, starting in any state, so like any precondition, if I apply BFS to that starting node, then the result will contain the set of all nodes reachable from the starting node. That's what this is saying. And then, yeah, we get simple proof of correctness here.
And the correctness is orthogonal to your complexity.
Yeah, so we prove, for every algorithm, we prove correctness using something like this, and then we additionally prove complexity, which I'm going to show here. These are all the helper.
But you can't prove complexity of something still got a sorry in it. You can't prove complexity of incorrect, or you technically could, I guess.
Yeah, I mean, every algorithm has a complexity, but like it might return something wrong, yeah. Yeah, so now we're saying that this function says that, you know, given some starting node running BFS on that starting node, the time that it takes is going to be, you know, in the specific cost model we gave, is.
Can you scroll up 2 lines?
Yeah.
Assuming that time is what you're defining right above this.
Time is general. It just, yeah, I mean, there's a lot of underlying infrastructure, but it's the cost. It's just returns the cost that we were talking about earlier from the cost model. But yeah, it's saying if you run BFS on this start, then the time it takes is going to be less than or equal to n squared. Yeah.
Just being a stripper's dumb person, but time and cost is only equivalent because in this case, your cost monad is addition over natural numbers. Because you're saying that if I said informally, oh, it breadth first search is n squared operations, whatever operations are, or n squared time, or n squared cost, they're all synonyms in this case.
Yeah, but if I were to take the cost of a circuit, it would be depth.
Bingo.
Right, yeah, yeah.
Okay, that's fine.
Yeah.
Because where you're defining time.
Yeah, yeah. So yeah, that's BFS. We have the algorithm, proof of correctness, and the complexity. I think I'm going to go through just the...
Assume with MATLAB already has like big O notation, so you can just literally rewrite this in a big O.
Yeah, yeah, exactly.
It look like
Yeah, yeah, for sure.
complexity.
Yeah, and then I could say that, you know, the graph reachability problem is in P, because I have this proof right here, right? Yeah, go ahead.
So, should that be interpreted in big O notation, or is it actually more specific than that? Like
It's more specific. It's not, I could stay in big O notation, but this is like exactly that.
Okay.
It takes,
It's a finite graph on n, yeah, I can never have more than exactly n squared operations.
yeah.
Okay, so if
Not
there
just
was like
asymptotically for any n.
some multiplier, like actually it's
Yeah,
like
like so if I
2
have a
n
graph of
squared.
2, it can
Yeah.
take more than 4 ops.
Yep.
So you can be very specific.
Yeah, and another thing you can do, I had a whole slide on this, but it was complicated, so I took it out. But you can prove like lower bounds. So we have a lower bound on sorting algorithms proven in the library, which states that any algorithm which is correctly a sorting function will take order of n log n complexity, and that's proven in the library. Yeah.
I assume you can prove like, you know, not only the degree, you can prove like coefficients of that function, like anything you can prove.
Yeah.
And then you can.
Well, because that actually seems quite useful when you're trying to compare different sorting algorithms.
Yeah, that was kind of part of the motivation. Is like, you know, like Lean. It obviously throws away, like there's a theorem in MATLAB, for example, that merge sort equals insertion sort because they're, you know, extensionally equal. But like if you care about complexity, that should not be the case, right? Yeah, yeah. So you could be able, we have both merge sort and insertion sort and their time complexities in the library. So yeah.
So like instead of doing less than equal n squared, you could do less than equal some other sorting algorithm.
Yeah, yeah, for sure. Yep.
And I guess if you like did have this CPU model encoded in the type, you could in theory write a library where you could just accept any contribution from anyone, and as long as they prove that it is less for all inputs,
Yeah, for sure.
don't need reviewers
There,
anymore.
right, there are timing attacks on regex libraries and stuff like that outside Lean. You
Yeah.
can use this to prove that you will not
Yeah.
have such attacks.
Yep. I'm gonna show one. You have a question?
This might, you feel free to answer saying this is for later.
Okay.
But is this the right place to develop an intuition for saying if you have a type of graph, like now I want to make a more specific claim that if the graph is always a Manhattan distance graph, which is like it's a 2D grid, and I had a parallel processor, then in these waves of computation and vectorized, it would be this many wall clock steps. Like I say, like not just any graph, but here's a graph with a more restriction on its type. It's going to magically kind of help me make rapid progress on reasoning about those two here.
Yeah, I mean, assuming all the complicated stuff he mentioned is formalized,
but that wasn't the point right
then
now.
yeah, you can just talk about whatever. You can just add properties to your graphs. Yeah, yeah.
I'd
Still
say-
have to write the proof though, right? It will not derive the proof.
That's what I was going to ask in the reverse was, did you have an example that was better than that silly one about saying, where might you say for a more, now take the same thing and annotate it with a, not just simple graph, but a more restricted class of graphs and get a different bound. You were the one still stating the bound is n squared here, less than equal to n squared. It wasn't like it was deriving that given a type of graph yet.
Yeah.
Or is that one of the goals?
Yeah, I mean, you could just add restrictions on your graph and reason about it the same ways, right?
Right.
Yeah.
But until I come up with a theory about what will be a lot tighter than n squared, the statement as written here is, Lean is out there proving that the total time will be less than or equal to n squared.
Yep.
That's all I'm saying.
Yeah.
There's a big for all graphs. And then
Yeah.
especially.
Yeah. Go ahead.
You scrolled past a lot of stuff. I'm just curious for a sense of what was hard to prove. Coming in with low lean experience, that was a lot of proof.
Yeah.
What was the challenge in proving some of these things?
These were, I mean, because the definitions are straightforward and it's not a difficult algorithm. I mean, there's a lot of stuff to prove just because there's a lot of helper functions and helper lemmas. It was mostly straightforward. I mean, some of it was a bit tedious, but I don't think there was any for this problem in particular, there wasn't particular roadblocks. Yeah, I mean the lower. Sorry, go ahead.
Harder or the
The complexity is easier because you're just adding everything up. The correctness, yeah, I mean, getting used to using MVC Gen, I guess. This is kind of my first time, yeah. But now we regularly use, for proving correctness of algorithms in this library, we generally use MVC Gen. But that took me a while to get used to because it's a new proof mode.
Given what you've done here, would you write your own tactic to help you with?
That could definitely be useful. I mean, generally for me, when I have to, writing tactics comes when I realize I've done the same thing repeatedly, and then I just write something to orchestrate that for me. So yeah, I think there's probably tactics in here that would make this shorter, but I haven't written any yet. Yeah.
Do you have any models of computation right now that are closer to trying to model what the CPU is doing, for example? Or what's the most complex class model that you have?
We do have Turing machines, if that counts. Yeah, we have Turing machines. We have classical arithmetic circuits. We have, I think Turing machine is the lowest level, and I mean it's simple because the Turing machine is a bunch of queries. It's reading and writing from a tape, right? So it's the same idea. Yeah. Yeah. You got something?
May I suggest looking into interaction combinators next?
Yeah, that would be cool. Yeah, I've seen them, and I remember you presented on them. I think they're cool. I just don't know much, but if there's something useful here, that would be very nice. Yeah. I wonder if it could be used for parallelism or something like that.
In my mind, it's closer to how hardware dynamics might be, because it's very, or in theory, it can be made geometrical,
I see.
embedded into these days.
Yeah.
And maybe.
Yeah, that'd be cool.
Is there compare with a provider,
With what?
like a provider of the certain program, and then how how it's compared to with your cost functions to actually how kind of matches with actual execution of the program,
I don't.
an interpretation of the provider spits out.
I don't think I understood.
For example, if you want to evaluate certain algorithm, so that you can use it. Now you can use a profiler to see how it's doing. So you can use these
Like an
things to
abstract
Profiler. I'm not sure. I haven't.
In debugging a regular program in an imperative style, you can just put counters in and profile it.
I see.
But here you're doing a profile over all possible.
Right.
It's Yeah, it's the right analogy, right? It's like a profiler, but embedded in the
Right.
in the program itself, which is a little bit crazy. But
Because like I feel like if you actually want to model it, like I don't know, maybe you want to verify profile is correct, or you want to know that what actually cost is like.
Kind of like the ultimate
Yeah.
hook system, because not just a
Yeah.
profiler, but a debugger,
Right.
a linter.
I see.
Can we still see time to see the next two examples?
Yeah,
The
for sure.
randomization and the bottom?
Yeah, I think the randomization is my favorite. Okay, yeah. So here's a bit how we can do randomized algorithms. And what's cool about it is that because you can take sums of functors, you can add randomness to any query. The idea is we have this random sampling query, and the single query is this sample, and you have to give it a distribution using this type PMF, which is it's the type of probability distributions on a type. So, and it actually itself is a monad, which could be a fun exercise to prove. But yeah, so PMF given a type alpha is the type of probability distributions on alpha. And what you can do is so if I'm calling bind, if I sample using this sample query, and then I call bind, that will pull the alpha value out of it, but you could think of that as randomly sampling according to this probability distribution, right? So I could take like PMF bool and like restrict it to the uniform distribution, and that's equivalent to a coin flip, right? So what's nice is you can sum this given all the other query types, like for example, the sorting queries or the graph adjacency query. You can take the sum, which is just literally like the point-wise sum of these type constructors, and then you've added this like random sampling ability to any query you have. And then you can write algorithms where in mid-algorithm, you can just like coin flip or some more general distribution, right? So yeah, that's a nice thing we can do here. So what we're gonna do is randomize quicksort. If you've seen quicksort, it involves taking a pivot, right, and then partitioning around the pivot and sorting recursively on each side of the partition. What you can do is you can randomly sample the pivot using this random sampling query. Yeah, so we know how quicksort works. And then, I can show the code. And then the complexity is a very difficult argument because we're reasoning about expected runtime, and then uses a whole bunch of mathlib probability theory. And but yeah, I'm gonna show it here. Can you guys see that? Okay. Okay. Yeah, these are some helper functions, but it's not like the nicest implementation, but it has the idea. So we take a list of, we take a list L, we pattern match on it. If it's empty, return empty, right? Otherwise, if it's X corresponds to some X's, the first thing we do is we randomly select the pivot according to the uniform probability distribution on the length of the tail, right? So this is just going to be some random index in the list, right? And then we do basically the regular quicksort after that. This is some like bookkeeping, but then we partition into left and right around the pivot. We sort the left and right partitions, and then we just append them together. And then we have to do some termination argument because the link.
Stuff for the termination.
Yeah, that was the thing. The nice like normal implementation of quicksort that would have been very readable. It just didn't. I couldn't convince the termination checker. I guess because But then this ends up being a short proof anyway. So yeah, the flagged stuff is just to keep termination intact. But that's the idea. We take the uniform distribution on the length of the list. We randomly sample some index from there. We partition around it, and then we sort recursively. Yeah, well, the non-computable part comes from the randomness, because it's like, I guess programs in PMF are non-computable because it's dealing with real numbers or something. Yeah.
Looking at PDF, not just like over a finite set.
Yeah. Yeah, PMF is like, so yeah, that's the quicksort. then we do correctness. This is a bunch of helper stuff. Let me find the. Yeah, so here's the final correctness claim. This is saying, given any precondition, if you run random quicksort on a list, you get an output which is a permutation of the input and is, this is saying sorted, right? We do induction. Basically, it's basically induction on the list. We call it MVC gen both cases.
Show the info view for that actually, just briefly.
Yeah,
so
for
like
sure.
before and after with MVC.
Yeah, for sure. Where's?
Enter will toggle.
Oh, yeah, I didn't know that. So yeah, induction here just does induction on the list. So the first case, so we have the empty list. It's not super interesting. And then MVC gen, does that make sense? Maybe this case is more interesting. But yeah, basically what MVC gen does is it decomposes the program according to all the binds in it, because the bind is like the main monadic structure, and it just like, yeah, it breaks it up that way. This is pretty unreadable, but yeah, cool. And then we do a runtime analysis. This is definitely the hard part because we're doing actual probability theory. Here you see these like number theoretic stuff. Yeah. Let's see, where's the final randomized?
Were all of these proofs done by hand, or was
No, they're the combination of myself and Claude. Yeah. Especially when we got into the deep MathLib probability stuff, I wasn't doing that. Oh shit. But yeah, this is the final bound on the expected runtime of random quicksort. If you want to take a read, it's yeah.
So with the extended rails, I assume.
Yeah.
So the
Yep.
inkling infinity.
Mhm.
But it's not it. It's less than.
Yeah.
Can you also model the worst case then and prove that runs into n squared?
Yeah, you should be able to. Yeah, I didn't write it here. Yeah.
And the difference in that is just your setup of modeling probability. Like you need some lemmas that help you understand what the worst case outcome could be. For
Yeah. Yeah. Exactly.
I assume it's in the expected runtime. Can you click on that? Can you see that?
The definition. Yeah.
The definition where they assume there is versus expected versus worst case.
I noticed you put
Yeah.
no duplication in the list also. Was there a reason for making it duplicate free specifically in the quicksort proof?
I think they just made it easier, but you probably should be able to prove it without that, right? Yeah, here's expected
It's
runtime.
integral, yeah.
Yeah.
Duplicate.
Yeah. Yeah, this was this was a lot of AI, but definitely the hardest proof I've done in this library. Yeah. Yeah. Then I'll show the quantum one. Yeah. So I don't know how much you guys know about quantum computing. I don't think I'm going to go through all the code, but the idea is that in quantum computing, the basic operations you're performing are like unitary maps on qubits. So the query type is just defining those unitary maps. So we have like, or what they call like gates. So we have the Hadamard gate, the poly X, poly Z gate. These are specific like unitary matrices, C naught. And then we have some called some like oracle. Yeah, and then the model. So I'm sure you guys obviously know MathLib and CSLib. There's also PhysLib. The semantics of the quantum queries come from PhysLib. This unitary of is saying like, yeah, you're getting the unitary map, which is defined as a type of linear operator in PhysLib. So this is allowing our syntax to correspond to actual unitary operators. And yeah, this is the function that we're using. This is kind of the classic example of a quantum algorithm that outperforms a classical algorithm. It's pretty contrived, but it's very cool how the complexity works. Basically, you're given a function of which takes in bit strings of length n and returns 0 or 1. And the idea is that you're querying the function. You want to check if it's constant or balanced. Constant meaning that it returns the same bit on every input. Balanced meaning is half true or half false. to do this deterministically, you'd have to check basically all the possible inputs, which is going to get you 2 to the n because it's n bit string. But in quantum, you can just do one call to the oracle, which is like, this is the sort of first example of a quantum algorithm that outperforms a classical algorithm. I guess I can show the code. But yeah, the idea behind it is you take in some basically empty, some all zero state. You apply this Hadamard query, which is one of the query types, to all of them. You call the oracle once, you apply Hadamard to the output, and then you get the answer. It's pretty magical, actually. And where's that algorithm? Yeah, Deutsch-Jose. So that's, yeah, literally what it's done. You take in what's called the zero register state, which you could just think of like all zeros. Apply Hadamards, Hadamard is one of the quantum unitary gates. You apply it everywhere, and then you call the oracle, and then you apply Hadamards again. And then that returns some quantum state, right? And then, yeah, we prove, and then we define the result. This is sort of the specification. This is an actual object from PhysLib. So we want to say that our algorithm, when interpreted by the semantics, will return this actual physics object, right? Which we show where, yeah, we show that here. And then we have, yeah, we show that here. This is saying that this is the Hoare triple. This is saying that the output of the algorithm is exactly that matrix, right? And then, yeah, we prove correctness. And then the thing we show at the end is that the time, which is time here, it just means the number of queries equals 1, which is interesting because the classical algorithm takes 2 to the n, right? So, yeah. I guess that is,
And then
sorry.
use a similar kind of statement for the classical case where you swap out quantum model for classical model, and I guess the 1 for 2 to the n.
Yeah, basically. Yeah, we don't have I guess it would be good to actually write that out. But yeah, we don't have the classical algorithm, but I think that would be nice. Yeah, go ahead.
I suppose then you could like define some class of algorithms that are faster on a quantum computer than a regular computer somehow. And
Yeah.
precisely characterize that.
Yeah, we do have basic quantum classes. Defining the like interesting ones actually takes some effort, and I'm not a quantum person, so I don't really know. But we have like BQP/poly, which is I guess simple to define. But then like the interesting ones are like BQP, and I don't really know how to define that yet, but we should be able to.
Yeah, we can get Scott Aronson on this.
Yeah, right. We've talked to some people for some reason there's a lot of people right now that are interested in quantum stuff in Lean. Very few people are taking this like syntactic approach to it. So I'm hoping this can be kind of a nice high-level abstraction for everyone else to use. But yeah, there's some big players in the quantum space that are looking at Lean actually. Yeah, sorry, go ahead.
So did I hear that like use that like the code above is the correctness or the proof of correctness?
Yeah.
So how do you know that that is correct?
Yeah, so that wasn't actually the proof of correctness. That was the proof that the algorithm, as it's written, corresponds to this particular matrix. We then prove that that particular matrix is correct.
Okay.
Yeah.
So how we know that that doesn't have a bug?
That the definition of the matrix doesn't have a bug? Yeah, that's kind of the specification problem. It's like, yeah, I claim that this algorithm is supposed to represent this matrix, and then I prove that it does represent that matrix, but whether or not that's the correct matrix is just the specification that can't be proven, right?
Oh, we can't? We don't?
Like, you can never prove that the thing you claim about the algorithm is the correct claim. You can only prove that it follows, that the claim is true, right?
Okay, so I'm a little bit confused. I just wanted to know that how this part of the code doesn't have a bug.
Yeah.
It's like when we do math in Lean, right? Like the
Right.
statements,
Right,
you have to make sure that matches the mathematical intent.
right,
And then
Mhm.
the rest of the proof,
right.
you trust the kernel.
But then like how the proof is actually correct? because-
it follows the rules of logic.
So if it's like if the Hauser, because you can like if you follow the rules of logic, you can derive the one conclusion. So the why we can be sure that that conclusion is correct.
That's like an incompleteness thing.
Huh?
Right.
So we actually know. So we're only working on the like problem that we know the correctness. Like we know the certain correctness.
You have like an axiom, right? I think
Right,
you're saying
yeah,
there's some
so-
construction
yeah,
of like predicates,
Right.
right? And the construction itself is either true or false, right? But we
Okay.
don't know if but we can't prove that the axiom is well founded, right?
So we were not working on the problem that we don't know the answer.
We can prove something that's like vacuously true, like it's true that I'm not a hamburger, right? But
Right. But I mean, like, for
No, I
example,
think what's
you
being asked
use-
is that Lean
Yeah.
itself cannot supply us with novel proofs of novel mathematical results. Because
Maybe
can
it doesn't
check-
have to be
check
normal.
existing
Like
proofs.
it can be like you can make one proof. Like even though we do mathematical proof manually, we can make a mistake.
Well, Lean is written such that, I mean, if we assume that, modulo any actual bugs in Lean's implementation, Lean is a proof verifier. So if Lean tells you your proof is correct, then your proof is correct, and that works by type checking. There's, what'd you say?
I was just saying and showing that something is false is equivalent to implying it's false, but that corresponds to constructing like a program that cannot be run.
Yeah, a program that doesn't terminate. Yeah.
Okay, so that it's this. Even though we don't necessarily know the answer, is that as long as we could construct that proof, then it should be correct.
Yeah, and if Lean compiles, then the proof is correct, assuming Lean is correct. But yeah, we all assume that Lean is correct. Yeah. Yeah, go ahead.
Double check, which parts came from FizzLib that you're building on? So M-state is.
Yeah, M-state is a density matrix, which is a term in, it's a quantum physics thing, which is defined in FizzLib.
But you weren't picking up like Hadamard gates from.
Hadamard gates, so Hadamard gates are in FizzLib. The Hadamard gate we have is, like I was saying earlier, it's just the syntax of the query. The model, the semantics of that is the Hadamard gate in FizzLib, right?
Okay.
Yeah.
I'm just trying to build that intuition back to you're saying like adjacent and ADJ
Yeah.
or the cost of an operation and the time of something.
Yeah.
Like the fact this is one step of actual physics time.
Yeah, so like
It's just the
Hadamard
interesting result here, right?
Hadamard is to adjacent as the actual Hadamard is to ADJ, right? Yeah. So these things all follow a very similar pattern, which is kind of what the point of this abstraction is like, So it's very often you'll be defining some query as some piece of syntax, and then you'll be evaluating it into some real mathematical object, and then your algorithms will be monadic programs with those queries, and your proof will say that the corresponding mathematical object is the one you wanted to construct, right? Yeah.
Have you ever considered amortized analysis of data structures?
I haven't. I think we've had like people in the community working on this, and I think there's some like professors out there who have their students helping us here, and I haven't like kept track of everyone that's working on it, but someone might be doing that. But like, yeah, I've been just trying to keep the infrastructure going and like having the right abstractions and things like that. But we have like people in the community that are like contributing algorithms and stuff for us. Yeah, like we have.
There's nothing
Sorry.
preventing it from doing amortized analysis, because that just means you're doing some expensive operation after.
Yeah, I mean anything you can state in Lean, you should be able to fit it in here.
Yeah, I guess I was just asking because I was curious, out of all the things you got on the left-hand pane there, kind of what was the more challenging thing to do? It sounds like the probability theory was pretty
Yeah, the probability was the hardest. I mean, again, at this point, this has become a kind of a group effort with a lot of people. Which ones did I even write?
What is KMP?
That's some strings. It's like substring search or something. I didn't write this, but it's an algorithm for searching for occurrences of a substring, I think.
Morris Pratt?
Yeah, Newton Morris Pratt. Yeah, sorry. Yeah, so I mean, I guess we could go through here a bit. We've got a bunch of. Here we have like complexity classes, bunch of algorithms here. So it's divided into algorithms, models. So here's like quantum model, comparison model, graph model, sorting, random sampling. These are our models, and then our algorithms are just like algorithms we've written in these models. So yeah, you see we have circuits and things like that. Searching through vectors. Yeah. Yep. Go ahead.
Are we at the portion of the time already, 20 here, to the random speculation questions?
Yeah, I mean
Where do you want to see this go, right? So tell us, get us excited about the future.
Yeah. So.
Do you want to finish the slides?
Yeah, I mean the slides are. I mean.
This is,
Okay. Yeah. Here's a bunch of stuff. We kind of just saw that. What's kind of in there already. Yeah, it's kind of straightforward. Some next steps. I guess that's a good spot. I think so. Yeah, my co-author kind of. Yeah, he kind of has been a lot of the vision for this. He's an algorithms researcher, and I think his motivation, or our motivation for this, is providing ways for people in like the algorithms and complexity community to formalize their work, because there really is no existing way of doing so.
Who's your co-author?
You know Shreyas? Yeah. Yeah. So the sort of the query combinator model as an idea was kind of his idea, and it was my idea to use free monads because I wrote the free monads. So that's how we sort of started working together. He was talking about his idea, and then I was like, oh, I think I just wrote this free monad library. I think you could use this. And he's like, that's perfect. And then that's kind of how this came to be. So we've been working on it for several months at this point. And yeah, but I think the goal is broadly for the algorithms and complexity community to be able to formalize their own work, which I think at this point we've shown it can be done in this. Yeah. So yeah, that's everything. Yeah.
So one of my practical application questions is, coming from computer security, Cedar is this authorization language from Amazon about can we approve some action in the cloud, say.
Yep.
And there's these string operations throughout it that have been difficult because you want to say conditions in security that are based on time of day or phase of the moon, or whether the tag is production machine or test machine or developer machine. And these are all strings. And so there's a bunch of claims that I've not fully understood about. Because the way they handle strings and map them back into sets, they can do these solvers and still come up with fairly bounded time constants. Because your worst case is that, yes, you have a policy language for deciding whether to allow an operation to go, but the permissions language is Turing complete, which a lot of competitors in the space are, but it's like, could be an unbounded worst case.
Cedar's not Turing complete, right?
Huh?
Cedar's not Turing
Cedar's
complete.
not, but a lot of the competitors or alternatives can be.
I see.
Right?
Okay.
So one of the things I was trying to understand was like, there are hard claims you want to make in a security policy environment, both one for constant time padding, like cryptanalysis and cryptographic libraries, want to say that, hey, this will always take within some very narrow bound of time, the same amount of time. But I don't know that necessarily is a great use for this. The other is that based on certain distributions of strings as actually seen. So given that I'm going to run this set of security policies, a few million examples, in this database of this cloud environment that I spent a couple million a year on, and there's these 14,000 kinds of tags, but the strings and the actual lengths of these tags this way, and these regexes are over here. So given like a regex library, what would I be able to use here to try and come up with concrete bounds, or conversely say, yes, you can run this security policy, but you have to now, as a result, go back and not have strings longer than this long, or all of these things.
So what could be nice is I know that Cedar has its whole specification written in Lean, and like, so if you have these algorithms written in Lean, what you can do is rewrite them in AlgoLean, prove the complexity about them, and then just prove that they're extensionally equal to the Cedar implementation, right? That's kind of what immediately comes to mind for me. So since everything is in Lean, that makes it really nice. It's not like you have to prove against the Rust or anything like that. Yeah.
How do you prove an extensionally equal to the Cedar? Is that like a solved problem?
Oh no, what I'm saying is Cedar itself has a Lean implementation, which is what he's talking about.
It has a defined.
So if he has some function in the Lean implementation and he wants to prove its complexity, you would just rewrite it using all this, prove that complexity, and then just show the two functions are equal, which,
Right, and that would be where I'd come up with hypotheses like a distribution function rather than being a random distribution or a sample. It would say, as long as all of your tags that are in your query policies are based on a prefix that are constant this way, and all of the tags you actually use in your company are prefixed this way, then this thing will always run in, ideally less than X nanoseconds.
For sure.
But in terms of even the cost function here, that's the big brilliant. Whereas other things where competitive or alternative languages, you'd like to actually demonstrate that if you use CEL, yes, you can express this in Lean that there's semantics for it, but because of the way it recurses, these are the screw cases where the performance goes out of unbounded or slows your system down.
Yep.
Sorry to ask. It was all basically saying, how do you run this thing? What are your potentials for running this thing backwards? You're saying, okay, given that I need to stay in some performance regime, not to get to the full compute vector, real circuits, which is hard, but at least even in this theoretical domain of saying, hey, I need to know these could be done in constant time. These won't overwhelm the system, but then you need to put these restrictions on your input data. Just didn't know if that's a frontier.
I assume that's just a fancier cost model because you
Yeah.
have a
Yeah.
string coming in, a regex, that's a function. The cost is now defined based on what's going in, right?
Yeah,
So
I
if
mean,
you have a very fancy cost function, then you can prove very fancy things about it.
I mean, the magical console experience of having an AI to help you do the proofs would be saying, given that I would like the bound to be here, what sorts of restrictions on the graph would I want to experiment until I get a working system?
So you mentioned swapping the function. So I don't know if I fully understand that part. Because let's go back to the sort you showed.
Okay. I don't really show a sort. You mean in the code?
Sorry, yeah. Sorry.
Oh,
What was the
sorry.
first
The random quicksort, or the BFS.
The BFS, sorry.
Okay.
The BFS, right.
Yeah. Should I show the code, or
I
do you
guess,
want to
yeah,
just see
I mean,
the
it has
slide?
an eval function, right? So you
Yeah.
can run this
Yes.
with the monads.
Yeah.
How does that compare actually at runtime to one written without the monad? Does the monad get like optimized away?
Oh, it's a good
Or you
question.
would swap it because you also mentioned like swapping with another implementation which doesn't have the monad, or you can just run it because the compiler would optimize it.
That's a good question. I don't know how the link compiler treats monads.
You can run you can run a test afterwards.
Yeah.
Show us like.
I suspect this will be slow.
Magic compiler could also, but yeah, I think by default we expect to be slow, but optimizing compilers are things.
Yeah.
The only way to find out is write AlgoLean and AlgoLean and then prove some latency.
Yeah. Right.
Oh yeah, that's right. You can prove it, but you can also actually run it probably.
Yeah.
With some examples.
What can you just compile it in Lean and then take the opcodes and then have the prover extend the proof to the opcodes?
Possibly. I'm not sure.
I mean, because then you could just, I mean, if you could, you want to prove it based off of the opcodes, so to see that the opcodes are equivalent to whatever you proved the initial proof with.
Yeah. I don't know. Yep.
So one like natural application that seems to fall out of this is, if you can come up with some like simplified cost model for like a CPU memory, stuff like that. Just going to a bunch of big companies and being like, hey, like here's this latency testing service, and we can provably like provide you this thing that guarantees that you won't have like latency regressions when you push updates to your code base or whatever, right? Like, is that something that you or people who you know are thinking about?
We haven't thought about it, but I think it would be good. I think what we're kind of working on like kind of academic contribution here. We're trying to write a paper on it, but I haven't thought about industry use cases. But potentially, yeah.
You would probably even keep your competitive advantage if you use your null proofs.
Yeah.
You didn't have to necessarily prove correctness. You said you might as well, or given the vibe, you would prove correctness and the complexity. But I guess to piggyback on the industrial case, if you're saying I've got some algorithm, I want to translate it into this framework, and I know that I've got a particularly expensive operation I need to run, I would like to reason about this doesn't happen too often. I assume you can say, assuming I've like implemented this correctly and I'm not going to bother proving it, I can say something about how often my algorithm is going to hit this expensive case.
Yeah.
And that would
Yeah. I mean, you could do something like define that expensive case as a query, and then your cost model just counts the number of time that query shows up.
right.
Yeah. Yeah.
What is that will provider does is that for you necessary correctness, at least profile where it shows that your operating your function is cost free for the CPU or like latencies.
Oh yeah, they are different. Like you can know some algorithm that goes
Yeah,
for a
it's
list
not-
once, no matter what it does, it's like constant linear time of the length of the list, regardless of its interpretation. It's just scanning elements, say, or at least, yeah, under like a trivial cost model, regardless of like what it's supposed to do.
Yeah, I believe that's, if I'm understanding, that's similar to how we prove the lower bound on sorting, because you can think of a model of the sorting query, of the comparison query, as just a permutation of the list, because an interpretation of what less than means on a list corresponds to a permutation of the list, right? So we're saying for the proof ends up saying that for any of these permutations of which they're in factorial, we fall within some bound. I guess that's similar to what you're saying, because it's not tied to any particular interpretation, right? It's purely a syntactic, it's a syntactic claim.
I
Right.
think it's the we saw with real time. So if we just real time profiling, if we're just looking at the latencies or performance of real time, we just average operation.
Yeah. Yeah.
So-
Yeah. I'm not. Yeah. Sorry.
I'd like to try kind of a yes and, I think building on this, the 2 or 3 ideas that's tossed out there. A successor paper, I would imagine someone might write in a few months, or at the rate we're living through this mathematical singularity maybe next week, is what does AlgoLean look like for SQL? So if I want to say, I have this set of queries, this set of tables, this set of indices, and that this is going to require at most 1 full table scan. Right, and that's a way that, coming from another literature that I'm a little more familiar with than the very large databases world and data warehouse world, that's a kind of performance question you'd like to do with a cost function that says essentially, how many times are you hitting in this relational algebra, this thing, and I might have another set of look-aside facts about whether this table is expensive or whether this one spills over, or in the third paper in this sequence would be saying, given I have a cluster of machines, this randomly distributed, this probability distribution function over latencies between hitting this index and scanning this index, or how long this join takes, actually given an abstraction of probability distribution over latency times and performance times, how long will this database query take? Is that a reasonable one you want to continue going down this path, or like at some point you're just taking this approach and pushing it too far?
It depends on the query, depends on the
Yeah.
But it prevents you.
But these are cost functions you can give it.
Yeah.
You can write the cost function.
Yeah.
The if state, you can make it very complicated.
Yeah,
Then your proof will be very complicated.
Yeah.
Like you just make it,
But you haven't looked at your actual SQL table sets and load those facts in, right? That's good about being
it's
the
a function, right? So
genericization.
you can make it as fancy as you want, but then you have to prove the theorem. And then the theorem gets really much harder when
That
the
goes down
function
to
is.
really you, but
Okay.
I think with all the kind of AI projects, it's better to start really going like crazy ambitious of like just ask it for a full CPU, and if it refuses, then maybe scale down, but up and down. with this kind
I
of
think
thing.
after this, everybody should download the library, go to the cost function, write your fanciest cost function, ask AI to prove
Give me
theorems
the
about it.
x86 spec.
Yeah, and see how when it breaks. 'Cause
I think like this.
Have a fund for tokens to just vibe and do like stuff at the
Yeah.
during these.
Yeah, I think in general this also is just a great playground for AI because everything is very like strict. You know what I mean? It's like you define your queries, you define your semantics, you define your costs, you prove the correctness, you prove the complexity. Like it's like a very direct set of directions for an AI, and I think you could think of any algorithm and it would figure out how to do it in here. You know what I mean?
you just gotta
Yeah.
tell it cannot touch the library.
Yeah, exactly. Yeah. Yeah, go ahead.
Given your free monad construction, you've got this representation of a program. Do you have any cases where you've transformed from one program representation to another? And so the reason I bring this up is
Yes,
to
actually.
answer that crazy question. Like, let's say you start out with a free monad that's like the program of like in some sense a link query. Like you've got a representation of SQL. The query planner is changing from one program to another.
Yeah.
And now you've got this different program, and then you could represent, if I've got a function as a query planner, and I've got my query plan, I can interpret my model.
Yeah, so we have reductions in here, which is exactly what I think you're describing. I'm trying to find it. It's like a function from your query type into some other free monad over some other query. And you can think of this kind of what you're saying. You can also think of it in the complexity theoretic sense of like a reduction is like, to perform this query, all I need is this program, right? It's like a function from queries to programs. But yeah, it gives you a way of like, and we have properties that it like preserves all the properties you want, right? So you get like a mapping from different types of programs into others. I'm trying to find I don't know where it is. It's in here somewhere.
What don't you have in here?
Right. Yeah, we've gotten a lot of help. It's actually pretty nice. But yeah, I think at this point we're just kind of trying to get people to contribute algorithms. Like we have a professor and a undergrad working on Union Find. I don't know the progress on that, but it should be interesting.
Are you looking for contributions from?
Yeah, absolutely. I mean, I think the setup, the framework is all there for people to kind of like. It's a starting point for anyone. You know what I mean?
His name, but one of Bob Tarjan's students or collaborators, they gave a talk with some update on Union Find, like at the beginning of the year, and I briefly mentioned Lean to him, and he seemed sort of interested actually.
Oh, nice. Tarjan's algorithm. Was he at Princeton? Is he at Princeton, right?
Yep.
Okay, yeah. Nice. That's cool.
Algorithmic research happening.
Yeah, no, I mean, if someone like that could get on here, that would be really cool.
Hasn't been all figured out.
Yeah.
They know that.
Apparently it was from knowing a bit about their improving how he even figured out he had the Ackermann bound. He said he had taken some logic classes too.
That's pretty cool.